We shall commence this module by studying about factor models. Models in the previous chapters explained the decomposition of the security risk into market risk caused due to economy-wide factors and firm-specific influences which can be diversified into large portfolios. In the index model, the return on market portfolio summarized the broad impact of macro factors. In fact, the asset's expected return can be influenced by a variety of risk factors as opposed to the market risk suggested by the CAPM or the capital asset pricing model. Consequently, a multi-factor model can be employed to measure and manage the exposure of securities return to each of the many economy-wide factors such as inflation rates, interest rates, business cycles, etc. The multi-factor model of securities return explains the risk premium derived from exposure to multiple risk sources, each with their own risk premium. The security market line of the CAPM would be generalized using the multi-factor model together with no arbitrage condition to imply a multi-factor security market in line of the APT. After studying the module, you shall be able to achieve the following 4 objectives. Number 1, learn about the factor models. Number 2, know the single factor model. Number 3, understand the concept of multi-factor model. And number 4, explain the multi-factor security market line. Let us now discuss about the factor models. The term factor here is referred to the economy-wide events influencing the securities return. The single index model and capital asset pricing model decompose the stock's variability into market or systematic risk that summarizes the broad impact of macro factors versus the diversifiable firm specific risks. At times, however, focusing directly on the crucial factors which are the sources of risk might be more useful rather than using a market proxy. Factor models are tools that allow us to explain and measure the different factors that affect a security's rate of return during any certain time period. A linear factor model assumes that the rate of return of a security or an asset is given by the following equation called as equation 1. Capital ER is equal to alpha plus beta 1 F1 plus beta 2 F2 plus beta 3 F3 till beta n Fn plus E, where Fk in k refers to 1, 2, 3, 4 till n, where k is greater than 1 and are random variables called factors. Alpha and beta are constants and E is mean zero term which is assumed to be uncorrelated among themselves and uncorrelated with factor capital F. That is, capital E brackets E is equal to 0 and capital E brackets E comma Fk is equal to E brackets small e multiplied by capital E into Fk, which will be equal to 0. The factors themselves are allowed to be correlated and are meant to simplify and reduce the amount of randomness in the analysis of assets or securities. Now we come to the single factor model. The simplest case of single factor model is the one where only one factor is considered. Here, the k, that is number of random variables in the model, is equal to 1. The Sharpe's single index model and the capital asset pricing model assume a single random variable, that is the return on market portfolio or the index summarizing the broad impact of macro factors. The market return reflects both the macro factors as well as an average sensitivity of firms to those factors. In a single factor model too, the assets returns variability is attributed to two sources, a common macroeconomic factor and the firm specific events. The common factor is constructed to have a zero expected value. The single factor model states that the actual return on security I will be equal to its initially expected return plus a zero expected value random amount attributable to unanticipated economy-wide events plus another zero expected value random amount attributable to firm specific events. The single factor model is expressed mathematically by the following equation called as equation 2. Ri is equal to capital E R1 plus beta 1 capital F plus EI, where Ri is equal to actual return on security I, capital E Ry is equal to expected return on security I, F is equal to deviation of the common factor from its expected value, beta I is equal to sensitivity of the firm to the common factor, and small ei is equal to firm specific disturbances. Let's take up an example. Suppose that the macro factor F is taken to be the news about the state of business cycle measured by the unexpected change in gross domestic product, and the consensus is that GDP will increase by 4% this year. Suppose also that a stock's beta value is 1.2. If the GDP increases by only 3%, then the value of F would be minus 1%, representing a 1% disappointment in actual growth versus expected growth. Given the stock's beta value, this disappointment will translate into a return on the stock that is 1.2% lower than previously expected. This macro surprise, together with the firm specific disturbances EI, determine the total departure of the stock's return from its originally expected value. Decomposition of securities return into systematic and firm specific events is convincing, but restricting the systematic risk to single factor is not. In fact, the systematic or macro factor summarized by the market return arises from a number of factors. The market return there depicts both market factors as well as the average sensitivity of firms to those factors. In single index model, we implicitly impose an incorrect assumption that each stock has the same relative sensitivity to each risk factor. If stocks actually differ in their beta relative to the various economic factors, then lumping all systematic sources of risk into one variable such as the market index will ignore the nuances that better explain individual stock returns. Indeed, there should be more explicit and clear representation of the systematic risk factors, allowing for sensitivities to each factor component. A fruitful modification of the single factor model would be to allow for possibility that different stocks show different sensitivities to various factors separately. A multi-factor model, which is a refinement of the single factor model, could provide for a better description of security returns. We next cover the multi-factor model. A multi-factor model, as is obvious, is one where the number of random variables k are greater than 2. Multi-factor model is no more than a description of the factors that affect a security's returns. Let us start with a two-factor model. The number of random macroeconomic factors in a two-factor is 2. Suppose the state of business cycle, which is measured through anticipated growth in GDP and changes in the interest rates. A decline in interest rates IR is considered a good news for stocks. These are the two most important macroeconomic sources of risk. The two-factor model describing the rate of return on security I is given by the equation called equation 3, referred to as Ri is equal to capital E Ri plus beta I GDP, capital GDP plus beta I IR, capital IR plus E1. The two macro factors GDP and IR on the right hand side, as you can note above, of the equation represents the systematic risk factors. Both these factors have zero expected values, similar to the case with single factor model. The coefficient of each factor measures the sensitivity of the return to that factor. These coefficients are also called factor sensitivities, factor exposures, factor betas, factor loading and asset exposures EI, as before, represents the firm specific disturbances. The multi-factor model clearly gives us a much richer way to think about the risk exposures and compensation for those exposures than the single index model or CAPM. We shall now discuss about the multi-factor security market line. The question that remains unanswered till this discussion is that where does EI come from? In other words, what determines the security's expected rate of return? One such model to answer this question is the security market line of the CAPM. It posits that the security's expected return comprises two components: the risk-free rate of return, that is, the compensation for loss in the time value of money, and a risk premium associated, that is determined by multiplying the benchmark risk premium to the relative measure of risk called beta. Mathematically, it can be represented by the following equation titled equation 4. Capital ER is equal to RF plus beta of capital ERM minus RF in brackets. Equation 5 can be denoted as E capital R is equal to RF plus beta of RPM, where if RPM denotes the risk premium of the market portfolio. Please note that the investors are not rewarded for the exposure to firm specific events, which is the residual term in equation 2. Equation 4 and equation 5 represents a simple security market line where there is only one source of risk that can be embedded into the market portfolio. However, one can recognize multiple sources of systematic risk. A multi-factor model now gives rise to a multi-factor security market line in which risk premium is determined by the exposure to each systematic risk factor and by a beta associated with each of these factors. It is a generalization of the CAPM equation, allowing for more than just one risk factor. The expected rate of return in a two-factor model, as illustrated above in equation 3, would be the aggregate of number 1, risk-free rate of return, number 2, the sensitivity to GDP risk, that is GDP beta multiplied by the GDP risk premium, and finally the sensitivity to interest rate risk, that is IR beta multiplied by the interest rate risk premium. This gives rise to the next equation titled equation 6, which is a two-factor security line. Capital ER is equal to RF plus beta GDP RP GDP plus beta IR RP IR, further denoted by a multi-factor SML equation called equation 7 through capital ER, which is equal to RF plus beta K1 RP K1 plus beta K2 RP K2 and so on till beta KR RPKR, where K leads to 1, 2, 3, 4 till N, ER is the risky assets expected return, RPK is the risk premium of the factor, beta K is the sensitivity of the asset to that factor, also called as factor loading, RF is the risk-free rate of return. Equation 6 is a generalization of the simple single factor security market line. In the usual SML, the benchmark risk premium is given by the market portfolio RPM is equal to brackets capital E RM minus RF brackets closed. But once we take the multiple factor of systematic risk into account, each with its own risk premium, we find that the insights are highly similar. Let's take up another example. Suppose we estimate a two-factor model for Jet Airways having a GDP beta of 2.2 and an interest rate beta of 0.6. Further, suppose that the risk premium for one unit exposure of GDP risk is 6%, while the risk premium for one unit of exposure to interest rate risk is 3%. Then, the overall risk premium on the Jet Airways stock should be the sum of the risk premium required as compensation for each source of systematic risk. The risk premium attributable to GDP risk should be the stock's exposure to that risk multiplied by the risk premium of the first factor, 6%. Therefore, the portion of Jet's risk premium, that is compensation for its exposure to the first factor, is 2.2 into 6%, which is equal to 13.2%. Similarly, the risk premium attributable to interest rate risk is 0.6 into 3% is equal to 1.8%. The total risk premium should be 13.2% plus 1.8% is equal to 15%. Therefore, if the risk-free rate is 5%, the total return of the portfolio should be 5%, which is the risk-free rate, plus 13.2%, which is the risk premium for exposure to GDP risk, plus 1.8%, which is risk premium for exposure to interest rate risk, and a total of 20%, which is the total expected return. Let us now recapitulate what we have learned so far. Number 1, factor models are tools that allow us to explain and measure the different factors that affect a security's rate of return during a certain time period. Number 2, equation for linear factor model is ER is equal to alpha plus beta F1 plus beta F2 till beta Fn plus E. Single factor model is a factor model where only one factor is considered. The following equation gives the single factor model. Ri is equal to capital E Ri plus beta IF plus EI. Next, the systematic or macro factor summarized by market return arises from a number of factors. Restricting the systematic risk to a single factor is not convincing. Next, multi-factor models seek to improve the explanatory power of single factor model by taking explicitly into account the various systematic components of security risk. Next, multi-factor model is one where the number of random variables or macroeconomic risk factors are greater than or equal to 2, followed by a two-factor model is the simplest case of multi-factor model. Equation for two-factor model is denoted by Ri is equal to capital E Ri plus beta I1 F1 plus beta I2 F2 plus EI. Secondly, a multi-factor security market line accounts for exposure to each risk factor contributing to the total risk premium of the security. And finally, a two-factor security market line is given by the equation capital ER is equal to RF plus beta I1 RP1 plus beta 2 RP2. This is all there to learn in this specific session. Thank you very much.